Thank you. First of all, I would like to thank the organizers for inviting me here, for letting me come here with Carolina, and for accepting the talk. So I'm going to speak about the joint project with Luca Chiantini, Giuseppe Favacchio, Brian Harbon, Juan Migliore, Thomas Schemberg, and Justyna Szpond. And for short, I will call this Politus, because there are three Polish members, 2 Italian, and 2 US-based members. And this is our logo. see on my t-shirt. I guess Giuseppe also has the same t-shirt, but he didn't show during the talk. So the logo is not just a logo, it has some meaning. I hope it will be visible after my talk. And the talk is based on 2 preprints. The first one is the same as Giuseppe was talking about, but not chapter 2, the rest of chapters. And the second is the new preprint from 2023. Both preprints are available at arXiv. So let me start with the definition of a Geproci property. So if we have a property P, whatever property you would like, and a finite set of points Z in the projective space over the field of complex numbers. So I will drop this assumption. I won't write C in the next slides, but all the talk is for projective n-dimensional space over C, or then 3-dimensional space. And we say that a set Z has a Geproci is a Geproci set if it's general projection, so a projection from a general point to a hyperplane, which is isomorphic to Pn minus 1, has the property P. So for example, we can think of the property P as being Gorenstein, and then we can speak of Gepro-Gorenstein sets. We can also say about P being a complete intersection, so Ci, and that is how Geproci sets come from. There are lots of open problems connected with Geproci sets. So they are very open, and the first is given a certain property, classify Geproci sets in Pn. So it is very, very general, and like this is the starting open problem. You can consider a property like being Gorenstein, and then you can try to classify Gepro-Gorenstein sets in Pn. Okay, you can note that Geproci sets are Gepro-Gorenstein sets, but not the other way around. And you can also try to classify Geproci sets in Pn. This is also very general. And in this talk, I would like to say something about Geproci sets in P3, since we don't know any examples in Pn, and we have some classifications in P3. So let's move to P3, and from now on, everything is going on in P3. So we say that a finite set of points Z is an AB Geproci set if its general projection to a plane is an intersection of curves of degree A and B. So we have a set of points in P3, and we project this set from a general point to a general plane, and the result lies on the intersection of 2 curves of degree A and B. This is an AB Geproci set. And we call the set, the Geproci set degenerate if it is contained in a plane. So here you have 2 curves. These curves are of degree 2. And our set Z contains 4 points, the intersection points. And then if you take any point somewhere in the space P3 and you project to another plane, the images of these curves would be the curves whose intersection is the complete intersection. So this is a very simple example, and we don't want to speak about this kind of examples. The question asked by Francesco Polizzi in 2011 was whether every Geproci set in P3 is degenerate. So is it true that all these sets are in fact sets contained in a plane and projected to another plane? So if we think about the answer, we may think about two curves in P3 intersecting. Because in the plane, it is what happens. We have two curves which intersect, and then we project, and the images of these curves are the curves which give this complete intersection. But the theorem of Giuffrida and Diaz from 1986 says that if we have two smooth, irreducible, non-degenerate curves in P3 of degrees A and B, then the number of intersection points is bounded by this number. So it is A minus 1 times B minus 1 plus 1. So it is not even close to A times B. So this is not the way how we can construct a Geproci set. Let me mention also the second part of the theorem. The maximal value is achieved if both curves are on the same quadric. I want to mention it because quadrics play a role here in this theorem. So as I have already said, the set of intersection points of two smooth, irreducible, non-degenerate curves in P3 of degrees A and B is not an AB Geproci set. So we have to look for another method to construct or to give examples of such sets. Okay, so let me tell you what was the answer. The answer was given by Dmitry Panov. The answer to the Polizzi's question was given by Dmitry Panov in the same year, in 2011. Let me recall, the question was, is every Geproci set degenerate? So do the point lie on a surface already, on a surface? And Panov said, no, it is not true. So there are sets of points which are not on a surface and are Geproci. And these sets are called grids. So what is a grid? Let me say what is an AB grid. An AB grid is a set of A times B points, which are of the form A intersected with B. So the intersection of two sets, and the first set is the union of pairwise disjoint lines, and the second is the union of, let's say, more pairwise disjoint lines, such that each lines from the set A meet each line of the set B in exactly one point. So if we consider the sets in P3, we will just see on a simple example how it looks. I took it from Brian's presentation. So here we see a 2-3 grid. So one set of lines is black lines, and the other set is the orange lines. So this is these are two sets in P3 having 6 intersection points, and these 6 intersection points are called the grid. And why grids are Geproci sets? So let us see on the example. We have this grid in the space, and if we project from a general point in a space to a general hyperplane, then we get the lines, the black lines are projected to black lines, and the orange lines are projected to orange lines. Of course, now the lines intersect, but Like this is not a problem because we look at the intersection point of the two curves. One curve is a black curve and the other curve is the orange curve. So the black curve intersects with the orange curve in 6 points, and this is the complete intersection. So the grid above is a Geproci set. Here it is a 2-3 Geproci set. Okay, so we may now consider whether there are some other Geproci sets which are not degenerate and not grids. We will call these sets non-trivial. So trivial if they are degenerate or grids, and now we are looking for non-trivial Geproci sets. And the modified question of polity would look like this. Is it true that every Geproci set in P3 is trivial? And if it's not trivial, is it possible to classify the Geproci sets up to projective equivalence? Maybe not all, maybe just for some small number of points. So let us look for on the first example. This is the example is the D4 configuration, and it was studied by Alessandra Bernardi, Luca Chiantini, Graham Denham, Giuseppe Favacchio, Brian Harborn, Juan Migliore, Thomas Schemberg, and Justina Spond during the previous Lefschetz workshop in Medico Terme. So this configuration looks like this. We have let's think of a cube. So 8 vertices. Here we have 6 vertices, and the 7 vertices, and the other one is hidden behind. So we take these 8 vertices, then we add the vertices which are the centers of perspectives of all the faces of the cube, and we add the middle point of the cube. So altogether, these are 12 points, and these 12 points form a D4 configuration. We may also give coordinates to the points, especially when somebody doesn't like to speak about the cube in the projective space. So this is a set of 12 points with such configuration, coordinates is the D4 configuration. And the D4 configuration lies on 4 disjoint lines. On different sets of 4 disjoint lines, let me tell you one set. So this is the set here on the slide. So if we have this D4 configuration in P3, we can project to a plane from a general point. And then, of course, if we project collinear points, we get collinear points in P2, in the hyperplane to which we project. So we may take the solid lines. Let's see, this is one line, then the other line, and this line. Oh, sorry, this line. These are the lines which cover 9 points of the configuration. And there is also one more line which goes through the front vertex, the middle vertex, and the vertex in the back. So if you project, the black lines go to black lines on the right-hand side. This line, which is not visible, the points are not visible, goes to the gray line. Because the points lie on a cone of degree 3, we have also the curve of degree 3 after projection. We can choose the lines differently, so we can choose, for example, the dashed line or the dotted line. So there are more possibilities to choose the lines, but in any case, after the projection, the 12 sets lie on 4 lines and a cubic curve. So this is a 3-4 Geproci set from the definition. and it is not agreed. Why it is not agreed? Because we cannot take the curve of degree 3 to be 3 lines because of the position of the points. We have also another example. It's an F4 configuration, which I cannot draw, but I can give you the coordinates of the point. This configuration consists of 24 points, so 2 times D4, the number of points in D4, and this is not the coincidence, because the points which are green here are exactly the points of D4 configuration. And the rest of the points are also D4 configuration, but moved somewhere away. So 2 D4 configuration grew up to an F4 configuration of 24 points, which lies on 6 disjoint lines, and is not a 4-6 Geproci set, and it is built up with 4-4 grid and on a quadric, and 2 sets of 4 points which are aligned. So in the case of D4 there was a 3-3 grid inside and a line outside. Now we have 4-4 grid and 2 lines outside of the grid. And we may ask a question: for which pairs of positive integers a and b, let's say that a is less or equal than b, does there exist a non-trivial Geproci set? So a set which is non-degenerate and it's not a grid. We know the theorem from the paper of Chiantini and Migliore, published in 2021, that if we have a set of non-degenerate Geproci, AB Geproci set, when both of A and B are at most 3, then Z is a grid. So the first, the smaller numbers that can occur as A and B, for the set not to be a grid, maybe 3 and 4. So the question is to classify all 3-4 Geproci sets in P3. And we have a theorem in the preprint from 2022 that if a set Z is a non-degenerate 3B Geproci set in P3, then there are 2 possibilities. The first one is that it is a 3B grid, and B is any number. We assume just B is greater than 3. And the other option is that it is a D4 configuration, so a 3-4 Geproci. So this means that there are no Geproci sets, like 3B Geproci sets for B greater than 4. And the proof goes through different cases, whether the points are in general position, linear general position, or lie on a twisted cubic. There are several cases which we consider, and we come to this result that if you have 3B Geproci sets, that it must be a D4 or a 3B grid. And so we ask a question: for which pair of integers a and b, which are both above 3, do there exist non-degenerate, non-grid AB Geproci set in P3? So if you are given AB, can you construct an AB Geproci set if this A is greater than 3 and B is greater? B is at least A. And we managed to give a construction for every pair of A, B, at least 4. The construction goes like this. We take the primitive n root of unity, and we take the set of points in P1, which consists of points 1, 1, 1u to the power, to the second power, and so on, up to 1, and u to the power n minus 1. And now we construct the product of these points. So we look at the points as row or columns vectors. We multiply them, and we get a 4 by 4 matrices by multiplying one by one every set, every point from A with every point from A. And we write these matrices as row vectors. So these are all the multiples of row vector matrices from A. And we consider the set Z to be the set of all these points, plus, and we consider also two other sets of points, y1 and y2, which are sets of collinear points. The set X is on a quadric. It is a grid, and the Y and Y1 are outside of this quadric. And the theorem says that if n is a positive integer, which is at least 3, then we have two options. If n is odd, then the set X plus Y1 and the set X plus Y2 are n times n plus 1 Geproci sets. And in case n is even, then also the set X plus Y1 plus Y2 is an n plus 2 Geproci set. And also the sets mentioned in the first part are Geproci sets. And moreover, the sets constructed by the standard construction are not grids. So we are able to construct an AB Geproci set when A is at least 3 for B equal A plus 1 and A odd, or for B equal A plus 2 or B A plus 1 or A plus 2 and A even. But we want to construct also the Geproci sets when the factors, the A and B, are different for more than 2. So we have this useful lemma. Then if we have a Geproci set which contains a Geproci subset, so we have an AB Geproci set and it contains a CB Geproci subset, Z prime, and a general projection of Z prime shares with the general projection of Z a minimal generator of degree B, the second number. Then the residual set, Z B's, which is equal Z minus Z prime, is an A minus C B Geproci. So this lemma allows us to construct the Geproci sets which are when the A and B are not different by 1, but by more. So as a corollary, we get that for every pair of positive integers, when A is at least 4 and B is at least A, there exists a non-grid and non-degenerate AB Geproci set of points in P3. So now I would like to tell you how this is linked to the weak Lefschetz property, and the link is via unexpected cones. So there will be a few words about unexpected cones, and then we come to weak Lefschetz property. I have shown you the sets D4 and D and F4. These sets come from the root systems, and they are proved to have unexpected cones. This is a paper of Harborn, Miliore, Nagel, and Teitler, published in 2012. And these sets are also non-trivial Geproci sets, which is shown in the paper. So the existence of the unexpected cones is equivalent to the failure of the weak Lefschetz property. So if we denote the unexpected cone property by C of D, so this is the property of the existence of an unexpected hypersurface of degree D and multiplicity. Then, by Macaulay duality, set Z satisfies C of D if and only if the weak Lefschetz property fails in degree D minus 1. So we have this set of points, P1 to PR, and we have the dual linear forms, L1 to LR, and we have another point, and then, and also the dual linear form to this point, and then the failure of the weak Lefschetz property in degree D minus 1 means that this multiplication doesn't have the maximal rank, and this means that the cone is unexpected. So now we may ask, because we know that these cones exist for example, for D4, for F4. We may ask a question: do all Geproci sets give failures of the weak Lefschetz property? And this is open. So if there is this cone, unexpected cone, we have the failure of weak Lefschetz property. But if not, we don't know if there are Geproci sets which don't have this unexpected cone. And this is how we come to half-grids. So all the sets we consider that were not degenerate and not grids were of the type that after projection we had some lines. And this is what we call a half-grid. So it is a grid in one way. So if we had a non-degenerate, non-grid Geproci set, we say that it is a half-grid if its projection is the intersection of two curves, and exactly one of the curves can be taken as a union of lines. So if both are the union of lines, that was the grid. And now we consider only one curve to be the union of lines. And as we have seen, the D4 is a 3-4 half grid, and it lies on 4 lines. And also all Geproci sets obtained from the standard construction are half grids. And so we may ask a question: is every non-trivial Geproci set a half grid? We don't have any general construction here, but we know 3 examples. The first example is H4 configuration, which is a 6-10 Geproci set, and it was studied by Paulina Wiśniewska and Maciej Ziemba in 2021. So this configuration also comes from the root system, but the maximal number of points on a line is 5, so this set cannot be covered by 10 lines. Also, there are 2 more examples. One of them is the Penrose configuration, which is a 5-8 Geproci set, and the other is a 10-12 Geproci set, and the 2 last configurations are connected to quantum mechanics. We don't know whether these examples are just the only ones or there exist some more. It will be interesting to, of course, to know this. So this is an open question. to decide whether there are other non-trivial, non-half-grid Geproci sets. Okay, but if we don't know how to deal with non-trivial, non-half-grid Geproci sets, we may try to classify half-grids. So how many non-projectively equivalent half-grids are there? And we were studying this topic in the preprint from 2023, and the result is the classification of 4-4 half-grids. So we assume that our set of points is a 4-4 half-grid in P3, and we discovered that there are two possibilities. So the first one is the anharmonic case, and then in this case the points are as on the slide, and these are the coordinates of the points. The epsilon is the primitive root of unity of order 6, and to visualize we can see that the points in the columns are aligned, and also the last row is the row of collinear points. So one possibility is that the 4 points lie on 4, let's say, horizontal vertical lines, and also the 4 last points lie on a horizontal line. And the second possibility, it's called the harmonic case. The points have coordinates as on the slide, and the coordinations are just the vertical ones. So the points in the rows, in the columns are collinear, and there are no collinearities in the rows. So how this is done, I'm not going into details. I will just tell you some tools we are using. So we consider permutations which leave the cross ratio invariant. We have 4 points on each line, so we may say about the cross ratio of this point. And we use the notation A, comma, J, comma, K, comma, L is the permutation which sends 1 to I, 2 to J, 3 to K, and 4 to L. So this is not a cycle, that's why the commas between the numbers. And with this notation, first, it is well known that the cross ratio is invariant under the Klein group. So this means that with this notation, if sigma is one of the 4 permutations listed on the slide, then the cross ratio is invariant. But there are these permutations or involutions, but there are also 2 more cases which leave the cross ratio invariant, and this is the harmonic and anharmonic case. So in the harmonic case, the cross ratio is one of the numbers -1, 1/2, and 2, and then we have 8 more permutations which leave the cross ratio invariant. And in the anharmonic case, we have 12 more permutations which leave the cross ratio invariant. So we study how the permutation of points on how the cross ratio on points on one line is read as a permutation of points on the second line, and so forth. Also, the proof uses the fact that if you have 4 lines in P3, then and they are not on the quadric surface, then there are 2 transversals of these lines. And also, what is very useful is that we can use this result from previous considerations. So if you have 4 lines, and our half-grid lies on these 4 lines, and we consider the set without one line, and then our points form a 3-4 grid. So how do we know it? The half-grid is a Geproci set, so if we take out a line, we get a 3-4 Geproci set, and there are 2 options. One is the grid, and the other is a D4 configuration, but the D4 configuration doesn't have 4 aligned points. So this must be it. And using this and considering how the permutations on how the points on the line go to the points on another line, using this cross ratios, we get to the theorem that gives that only this harmonic and anharmonic case. Let me go back to this. So only this harmonic and anharmonic case are half-grids, so these are 2 different types of half-grids, which are not projectively equivalent, and these are the only possibilities for half. So what can we do now? We can try to classify the 4B half-grids in P3, and here we also have these transversals, so we know how to start at least. And the open problem is to classify AB half-grids, where A is at least 5 and B is greater or equal than 8. So this is all. Thank you, and I hope now you know that this logo is the D4 configuration is somehow in this logo, and so you'll know why we are wearing these t-shirts. Thank you.